right, hey everybody. So I'm not here today. I just want to go do a quick rundown of some of the math and some of the theories and pictures behind titrations. Again, you've already went over this, but I need to go over it one more time because again, with titrations, the whole point of them is not to get light pink. All right, it never was the goal. It never will be the goal. The light pink color is only a visual indicator, hence the term indicator. It's only a visual indicator for humans to know when your, in this case, acids and bases, when your acid in the flask is completely neutralized. That's it. So the issue with, oh, I got light pink, cool. Well, if you didn't measure the correct amount of acid, your measurements are completely wrong, or you're swirling your acid and you take it out from under the burette and the burette is still draining base on the paper or on the table, and you're like, oh, look at me, I got a perfect light pink. Well, you're losing base, so you're losing data, so your data is trash because, yeah, you may have gotten light pink, hooray, but your data is garbage because you're losing base from the burette. So again, if you were an actual, chemist in a lab or whatever, doing real, doing this as a career, and this kept happening, you'd be fired. Just saying. So again, if it leaves the burette, it has to go in the flask because that's how you measure how much base you use is from reading the burette. So again, when we do the math, just know that if your math is off, if you feel like your numbers are a little weird, maybe it's because you didn't measure things properly in the lab. Maybe you lost some data throughout the process. So again, I'll chat about the math in a couple minutes. But again, just want to go over the theory behind all this. So again, the whole point of the titration is to completely neutralize, in this case, acid-base titration is to neutralize the acid in the flask with the proper amount of base so that you can do the math to work backwards to figure out the concentration of whatever you're trying to solve for. So as a visual, again, let's say that this is when my titration begins. So when I have my acid in the flask and I'm swirling just the acid, you have a bunch of H+. And with the indicator in there, it's clear because the phenolphthalein is clear in acids. And in this case, the pH is, I'm going to say it's around 1. All right, so very low pH. This is before you start. So while you titrate, again, you drop that base. Let's say you drop a single OH minus ion, so a single hydroxide ion. What happens is that hydroxide matches up with one of these H pluses and it makes water. All right, but you can see there's still acid in here, which is why you had to keep on adding the base. And as you added the base, the color, the pink color, would persist for a longer period of time because there's less acid in the flask. So it takes a while, it takes longer for the OH to find an H+. Again, I relate this to if you're going to ask someone to prom, I know prom's over, but if you're going to ask someone to prom, the closer you get to the prom date, the harder it is to find a prom date. So if prom is next week and you haven't asked anybody yet, well, there's not going to be as many people who want to go because it's getting closer to the day. So just like in this case, the less acid you have, the longer it's going to take, the harder it's going to take, the harder it is to find an OH and H connection. So in this case, the pH is around 1.1. So it's slowly getting higher, but not perfect, not perfectly neutral. So when you're perfectly neutralized, this is why it's immediate. Because right when you have the perfect amount of hydroxide and acid in the flask, you get a perfectly neutralized solution, which is good. So in this case, the indicator turns a light pink, lightish pink. I'd say the lightest pink ever. We get a pH of roughly 7. So it's perfectly neutralized. And again, this is hard to get because any extra base that you add is going to ruin the pH and it's going to ruin your data. So the reason this perfect reaction, this perfect neutralization works is because acids and bases completely neutralize each other. And you could use a balanced equation, and stoichiometry and mole ratios to work through, basically to work backwards to find out how much of the unknown substance you must have had in a flask or much must have used in your burette. So this is your perfect endpoint. The ruined titration is when you add too much base. Now, so I think I saw some people in lab add more acid to this. Then it's like, oh, I'm going to add more acid. Yay, I got the light pink. Well, you didn't measure how much more acid you used. So it doesn't matter. You kind of ruined the lab anyways. So again, this is over titrated because you have way too much base in here. And again, even an extra couple drops is enough because just like over here, a little extra acid really made the pH low. So a little extra base makes the pH extremely high, roughly 13 or so. So it's ruined because the phenolphthalein again turns your base crazy dark pink. You've over titrated it, and so therefore, when you read your burettes, the amount you have used is not true for the perfect ratio, which should have been neutralized, which is your light pink in the phenolphthalein. So again, that's why we were looking for this perfect color. Okay. But either way, you're doing the math. So again, for the math, like I said, it's nothing you haven't done before. Look back at old things, okay? For honors chem, to do day one's math, you have to do a very generic gram to mole conversion. Okay, we've been doing that since January. Then you have to do a mole to mole conversion, so stoichiometry, but it's a 1-to-1 ratio, so pretty straightforward. Then you have to find the molarity of your NaOH based on how many moles of it you have and how many liters, don't use milliliters, okay, liters of NaOH you used. So again, moles over liters is your molarity, and it should be closest to 0.1, all right? And then you can do day two's math because you used whatever that molarity is, that concentration of base, you used that in day two's labs, the HCl titrations. So you're going to use that for the molarity of your NaOH, and then follow the step-by-step procedures for finding out the HCl concentration, and we'll figure out what it should have been in a day. Fun. And then in 300 chem, you just didn't finish your first ever titration. Just go through the step-by-step procedures on how to get that acid molarity. We've done all this before. Okay, so with all the members of your lab group, all your brains together, you should be able to figure out how to do that. It's stuff we've done before. There's no straight up titration equation. All right, so it's not like I'm not teaching you something. We've done it before. All right, you may have to write out a balanced equation. We've been doing that since January. You'll have to you have to find out how many moles of NaOH you used. But I gave you the molarity equation because you know the molarity and you know the volume in liters. Yay for algebra. You can solve for moles. All right. We're doing that since we did density first semester. So solve for moles. And then you can use mole ratios to solve for moles of acid. And you know how many mils of acid you use. So you have moles of acid and liters of acid. That's why the molarity equation is given. So moles over liters. So it's a process. We've done it all before. All right. So the next day, I'm not going to re-explain it because this is the explanation. We've done it all before. Again, with all the brains in your lab group, you should be able to figure it out. We've done it before. I'll say it again. So take your time. All right. But that's all we're doing. So it's math day. Get that figured out, and we'll do the rest later. Woohoo.